Alright, so we've been talking about magnetic fields and trying to visualize what these magnetic fields look like. Now, one thing that might still be a question that you have is, okay, we understand what a magnetic field is, but we don't understand what magnetism is and what produces magnetism. Okay, so what we're going to do now, and what we've got in front of us here, is we've actually got an electromagnet that was constructed a couple years ago, and we're going to use this to try to figure out what the source of magnetism is and how can I make something into a magnet. So just to start off with, I'll just explain what this actually is. This is actually the actual core, what we call the core of the electromagnet, is just a retort stand. It's steel. It's made out of iron. We know that iron is, well, it could be ferromagnetic, but in most cases it's paramagnetic, like these paper clips here. And it's no surprise that this retort stand itself is not ferromagnetic. So it is not a natural magnet, and we can sort of, I guess, confirm that by trying to pick up some paper clips, and we see that it picks up nothing. I guess that one sort of picked it up a little bit. I think it just got stuck on there though. It's not ferromagnetic. Okay. Now, what's going to actually happen here is we're going to, you can see I've actually connected it to a power supply. And so what we're going to see is that as we pass current through the electromagnet, well, it's not an electromagnet yet, as we pass current through the green wire there, it's going to actually turn the retort stand into a magnet. So let's go ahead and do that. Now, the power supply, I'm just going to put it on 2 volts. And now let's do the same thing and see if we can pick up some more. Oh, look at this. We see it's a significant change. And in fact, the higher the voltage is on the power supply, the more current that's going to run through the electromagnet, and ultimately the stronger the magnet is going to be. Now, I've only got 2 hands here, unfortunately, one to hold the camera and one to hold the electromagnet, so I can't actually I can't turn off the power supply, but if I did, we would see that it would very quickly drop all of the paper clips and it would lose its magnetic properties. Now, there would be a little bit of residual magnetism there, but it would drop off very quickly. Okay, so I guess at this point we need to draw some conclusions for this. So it would appear that before the current was passed through the retort, through the green wire, that the retort stand was not magnetic, and after it was passed through, it obviously became an electromagnet. So clearly passing current through the green wire had something to do with it becoming a magnet. Obviously there's some sort of relationship there between electricity and magnetism. And we can sort of think about, well, what is electricity? And electricity is the movement of charge. It's moving charge. And so it would seem that when we have moving charge, that we get a magnetic field that's produced. And in fact, that is the source of magnetism, ultimately, is moving charges. Now, we actually know that moving charges are really, well, each charge has an electric field. And so if I move a charge, I've actually got a moving electric field. And it turns out that a moving electric field is in fact just a magnetic field. So this sort of answers one of our questions, and one of the things that maybe we've been wondering for a while, which is, well, what is magnetism? And ultimately magnetism is just a moving electric field. It's produced by moving charges. And that's why once we attach the green wire to the power supply and we get current that moves through it, we get charge moving through it, that moving charge produces a magnetic field. Now, some people might sort of say, okay, we accept that, but that raises other questions, because we know that everything in fact has moving charges in it. This table has moving charges in it. We know this. It's made up of atoms. Inside the atoms we have protons and electrons, and they're moving around. And so then the question is, okay, well, obviously we had an electromagnet over there. It was magnetic. Moving charge produced magnetism, but I can see that this magnet is not at all attracted to the table as we would expect. And so then the question becomes, okay, so if magnetism is produced by moving charge, then how come everything is not magnetic? And it turns out that the key with magnetism is that every single, and the source, remember, is these little tiny charges, these little electrons and protons. It turns out the electrons are actually about 1,000 times more powerful in terms of the magnetic field that they produce than protons. So we're going to sort of, it's not that protons don't produce a magnetic field, It's just that we're going to focus on the effect of the electrons just because it's so much bigger. And it turns out that each electron then is sort of like a little tiny magnet. Okay? Each one's got a little tiny magnetic field. Now this magnetic field is so small that you would not even be able to measure it. But if the magnetic field is just like any vector, because ultimately when we talk about a field, we're talking about a vector field. Remember that if vectors are in the same direction, that they add up. And so if the magnetic fields that were produced were in the same direction, the magnetic fields would of course add up. And if we had a lot of electrons that were all moving the exact same way, and we got a magnetic field produced that had the exact same direction, they would sort of add on top of each other. And of course the opposite is also true, which is that if they were moving in different directions, we could actually get a cancellation of the fields. And that's actually what's going on inside the table, or inside you, or inside most objects, is that the charges are moving, but they're moving fairly randomly. And so all the little tiny magnetic fields that they're producing are pretty much cancelling out. We're getting a very, very small, unnoticeable magnetic field. Now in the situation with our electromagnet over there, the charges are actually moving in roughly the same way, right? Because of course the red wire is connected to the positive terminal, the black wire is connected to the negative terminal. And so we're actually getting current and the movement of charge, and the charge is moving through the green coil in very much the same way. And so all those electrons, which is each one of them is like a little tiny magnet, it's got a little tiny magnetic field, and they're all adding together, and eventually it's becoming something that is actually noticeable and is big enough that it can actually attract other things and things that are paramagnetic, like the paper clips. And that then raises another interesting question, which is, well, what's going on with the paper clips? How come they become magnetic when they're placed in the presence of a magnetic field? Well, it turns out that what's going on is that all of the particles inside the paper clips there, they start off fairly random in their orientations, so we're not getting any sort of significant magnetic field. But then as soon as I put a magnet close to them, like so, well, what that does is it very quickly sort of aligns all of the different electrons and all the different atoms inside the paper clips, and so all of a sudden now they are all actually roughly moving in the same direction, and so we are getting an appreciable magnetic field that's produced there. So that's what's going on with things that are paramagnetic, is that they start off not aligned, but when I actually put an external magnetic field and it comes close to them, it actually aligns them so that they are and they become magnetic. Now something like this bar magnet here, which is ferromagnetic, it's starting off with all of the different sort of electrons and atoms. They are all aligned in the same way, and that's why it produces a magnetic field. Okay? Alright, so the last thing I want to do is just talk a bit about the magnetic field that is produced by this electromagnet. Now, right now, the power source is off, so it's not an electromagnet. Let's go ahead and turn that on. Okay? And what I'm going to do is clearly one side of the electromagnet is going to be the North Pole, and the other side is going to be the South Pole. Okay? Now, the way I can sort of determine which one is which is I'm going to use this bar magnet, and I know that the North Pole of the bar magnet will be attracted to the South Pole of the electromagnet, and I know that it's going to be repelled by the North Pole of the electromagnet. So let's test this side first. Okay? Now, there's a very strong attraction. I can already feel it. It's actually hard to sort of keep them separate, and it's very strongly attracted to this side of the electromagnet. So clearly this is going to be the South Pole of the electromagnet. And, well, just out of interest, let's test out the other side of the electromagnet. So again with the North Pole, and I can see that it really does not want to go in there. There's a strong repulsion there. So what this tells us is that, well, this is going to be the North Pole because it repelled the North Pole of the bar magnet, and this side over here is going to be the South Pole, okay, because it attracted the North Pole of the bar magnet. Now it turns out there's actually a way that we can determine this without actually having to use the bar magnet, and it is called the right-hand grip rule. There's actually two different versions of the right-hand grip rule. One is going to be applied in some situations, and ultimately it's going to be applied in a situation where we've got a current carrying wire, and my thumb of course will point in the direction of the current flow, and my fingers will then trace the magnetic field lines. That's one version of the right-hand grip rule. Now another version, the bit that's actually applicable to electromagnets and solenoids, is it uses the same setup, but my fingers and my thumb are different things. When we're talking about an electromagnet or a solenoid, my fingers are going to actually trace the current direction, okay? And my thumb is going to then point in the direction of the North Pole that's created. Now, the current in this case, so we can see that this is connected to the positive terminal, and so I trace this red wire around here, and I can see that the current is going to flow through here, and it's actually looped behind the electromagnet on this side. Okay, so just to make it a bit easier for myself, I'm just going to actually put my hand underneath it, and I can see that now my fingers are curled around in the direction that the current is actually going to go. So it's going to actually go behind the electromagnet and around and around and around. So my fingers are going to trace the direction that the current flows through the electromagnet, and as I said, my thumb is then going to point towards the North Pole. And in fact, that agrees with what we actually found when we tested it with the bar magnet.